When an earthquake occurs, seismologists create graphics of focal mechanisms, informally referred to as beach balls, to show the faulting motions that produce the earthquake. The focal mechanisms are based on the direction of the first arriving P wave. Let's investigate the patterns of P wave arrivals that result from different faulting mechanisms by first considering a strike-slip earthquake. When an earthquake occurs, seismic waves radiate away from the epicenter in all directions. The parallel green lines in the northwest and southeast quadrants have been compressed during the earthquake, and the northeast and southwest quadrants were stretched. Let's look at the P waves moving away from the epicenter. We will insert slinkies to demonstrate and exaggerate the compression and dilatation features. Northwest and southeast of the epicenter, the rock is compressed, and the first arriving P waves at those stations are pushes away from the epicenter. Northeast and southwest of the epicenter, the rock is stretched, and the first P waves are pulls toward the epicenter. The dilatational and compressional arrivals are often shown as plus and minus signs, respectively. With observations from many stations, we see two quadrants of compressional arrivals and two quadrants of dilatational arrivals, separated by perpendicular nodal planes. To simplify the illustration, compressional quadrants can be shaded, and dilatational quadrants are left unshaded, producing a P wave first motion pattern that looks like a beach ball. Notice that this pattern of dilatations and compressions can be produced either by right lateral strike-slip faulting on a north-south fault plane, or left lateral strike-slip faulting on an east-west fault plane. Therefore, you must use geological knowledge of the region to decide which nodal plane is the fault plane. For example, if an earthquake with an epicenter on the San Andreas Fault had a focal mechanism that looked like this, the most likely choice would be that the fault plane is oriented northwest to southeast, parallel to the strike of the fault we observe at the surface. Now let's consider a right lateral strike-slip earthquake on the Kane fracture zone in the Atlantic. This earthquake will produce compression in the northeast and southwest quadrants and dilatation in the northwest and southeast quadrants. Since there are no nearby seismometers, the P wave first arrival patterns are observed at distant stations. Seismic energy travels away from the earthquake in all directions, so we need to consider the three-dimensional geometry of the ray paths. To do this, it is convenient to imagine a sphere, called the focal sphere, surrounding the earthquake hypocenter. Rays that travel to distant stations will radiate from the earthquake through the lower hemisphere of the focal sphere. To keep things simple, let's look at two cross-sections at more or less right angles. First, make a vertical cut into the earth through the hypocenter in a northeast-southwest orientation. P waves leaving the earthquake and traveling to Lima, Peru in the southwest quadrant, or to Madrid, Spain in the northeast quadrant, will have compressional first arriving P waves that push up away from the earthquake and are observed as an initial upward vertical motion on the seismograms. The second cross-section will show P waves traveling to Detroit and Seattle in the northwest quadrant and to Cape Town, South Africa in the southeast quadrant. These will have dilatational first arriving P waves that are pulled toward the earthquake, observed as a downward vertical motion on their seismograms. By examining first arriving P waves at many stations over a range of azimuths and distances from the earthquake, we can determine the pattern of compressions and dilatations on the lower hemisphere of the focal sphere. As we have seen, a strike-slip earthquake produces a crossing pattern of approximately vertical faults, or nodal planes that separate two compressional and two dilatational quadrants. Now let's look at the pattern of compressions and dilatations that result from an earthquake on a normal fault, like on the east side of Steens Mountains in the Basin and Range Province. The block on the east side of this fault has dropped down with respect to the block on the west. Viewed in cross-section, we see that compressional first arriving P waves will radiate to the east and west from the hypocenter at shallow and intermediate downward angles. Dilatational first arriving P waves leave the hypocenter at a steep downward angle. The resulting focal mechanism has perpendicular nodal planes that cut the lower hemisphere of the focal sphere in an orange slice appearance with compressions on the outside and dilatations in the center. This is the focal mechanism signature of an earthquake on a normal fault produced by extensional forces. Because of the way the fault plan intersects the bottom of the focal sphere, the boundary between the regions on the focal mechanism is curved. Finally, let's consider a thrust fault, like that beneath Sierra Pie de Paulo, within Sierras Pampeanas of northwest Argentina. This is a west vergent thrust fault, wherein the block on the east moves up and over the block on the west. Viewed in cross-section, we will see that dilatational first-arriving P waves radiate to the east and west from the hypocenter at shallow and intermediate downward angles, whereas the compressional first-arriving P waves leave the hypocenter at steep downward angles. The resulting focal mechanism has perpendicular nodal planes with the same orange slice appearance observed for a normal fault. However, for a thrust fault earthquake, dilatations are on the outside and compressions are in the center. This cat's eye focal mechanism is the signature of an earthquake on a thrust fault produced by compressional tectonic forces.